This is chapter 6, electronic structure of atoms. Wave nature of light. So Webster's dictionary defines a wave as a disturbance or variation that transfers energy from one point to another in a medium. So one way to think of it is you can see in a wave in a large audience, the wave travels around the stadium, but if you look at each individual person in the stands, all they're doing is going up and down. So there's no net motion for the particular person. So if we look at a wave here, we have displacement versus distance. Displacement versus distance. We see here the amplitude is the maximum displacement here in y, how high the wave goes or how low the wave goes. We have the frequency, nu, is how many times if I set a point here on the wave, the frequency would be how many times the wave passes through that particular point per second. And wavelength, lambda, is the distance between two identical points. So from here to here would be considered the wavelength between two identical points. And I'll use the term angstrom, which is the same as 1 × 10 to the minus 10 meters. So here we have the electromagnetic radiation spectrum. If we look here on the top, we have the wavelength, and we have larger wavelengths on the left-hand side of the table and smaller wavelengths on the right side. Correspondingly, which we'll talk later, the smaller the wavelength, the larger or the higher the frequency, and as we have longer wavelengths, the shorter or lower the frequency. These are some examples here. Going from left to right, we have radio waves, then microwaves, infrared, IR, visible, which we are accustomed to with our eye being the detector, and then UV rays, soft rays, hard rays, gamma rays. And as we know, the gamma rays and X-rays can be a bit more dangerous for us because the wavelengths are very small, and they so small that they can actually penetrate between our skin molecules and therefore cause chemical reactions within our body. Versus radio waves, they have longer wavelengths and therefore less harmful to the human body. So as I mentioned in the previous slide, we have the visible range here, approximately 10 to the minus 6 meters. We have the shorter wavelengths here for the purple, and we have the longer wavelengths at 750 nanometers for red. Important equation that you'll be using is c, which is the speed of light, constant of 3 × 10 to the 8 meters per second, is equal to the frequency times the wavelength. So hopefully a straightforward question. If the wavelength of red light is 455 nanometers, what is the frequency? We use c equals lambda times nu. We want to isolate nu, so nu is equal to c over lambda. Lambda is given 455 nanometers. We have to convert that to meters. So on the top, we have our constant, 3 × 10 to the 8th meters per second, and 455, 4.55 times 10 to the minus 7 meters gives us 6.59 times 10 to the 14 seconds to the -1 or hertz. So Planck's quantum theory says that the atoms and molecules can only absorb or emit energy by set quantities. We call the smallest quantity of electromagnetic radiation that can be absorbed, we call that a quantum. So, which states that electrons can only live in certain, we call them shells, or certain levels, we'll say energy levels. N equals 1, N equals 2, N equals 3. So it's like walking up steps. You can only step on certain steps instead of this increased ramp here. So energy is quantized, meaning the electron can live on N equals 1, N equals 2, N equals 3, but cannot live in between these levels, cannot live in between. So we have these particular energy levels. E equals h nu. H is Planck's constant, 6.63 times 10 to the -34 joules times seconds, or 6.626. We can also use this equation with our previous equation for the speed of light, because c equals lambda times frequency. So there are times when we can plug this in and isolate frequency and put it in here to give us this next equation, E equals hc over lambda. So a photon, a packet of energy, as an example, has a wavelength of 500 nanometers. Find the energy of the photon in joules. So we use this equation, which is circled in orange. We plug in the values, Planck's constant, speed of light, and our wavelength, which we have to convert to meters, and we calculate out 3.97 times 10 to the -19 joules. You can pause the video now and try for the following equation. Calculate the energy of a photon with a wavelength of 5 times 10 to the -2. So again, we use E equals hc over lambda. We know h, 6.63 times 10 to the -34. We know c, the speed of light, 3 times 10 to the 8. These are constants. And we need to convert 5 times 10 to the -2 nanometers to meters. And that comes out to 5 times 10 to the -11 meters. So when we multiply this out, hc, we get 3.9 times 10 to the -15 joules. The photoelectric effect, work by Albert Einstein, refers to the emission or ejection of electrons from a surface of a metal in response to incident light. In this example, we have metal here. We shine some light on it. The electrons from this metal will come off. And there's a collector plate here on the left, which will cause a flow of electrons where you can actually measure the current. And what happens here on the emitter plate, there's a particular, if these are atoms on the metal plate, the light hitting this metal plate, the electrons here will break free from the metal if it's given with a high enough energy, shot with a high enough energy, and it breaks its barrier, its work function, which we'll talk about in a second. So we have here the electrons are knocked out. They must overcome the work function. So like I said, the work function is like a wall, or like how high you have to jump. For instance, to make a slam dunk, you have to overcome some barrier or overcome some wall. We have here the energy, or E equals hv, how much energy you have to add, or how much is added to the metal, and this is the kinetic energy, the energy of the ejected electron once it overcomes that barrier of W. So the example here, the work function of strontium metal, strontium again, if you recall, Sr2 plus is 3.22 times 10 to the minus 19 joules. That is the wall that will be given to you. Calculate the kinetic energy of ejected electron if light of frequency 1.5 times 10 to the 15 hertz is used to irradiate the strontium metal. So we want to isolate kinetic energy here. So we can rearrange the equation to have h nu minus the work function. So we plug in the values, and this is the energy of the electron once it leaves the metal, 6.72 times 10 to the minus 19 joules. So using the information of the work function for strontium, we can solve the next question for the above. Determine the minimum frequency of light needed to release an electron from strontium. So in this case, the kinetic energy will be 0, and we just need to isolate h nu times or equals to E. Here anything above will have a kinetic energy, so we can set it to 0. So h is 6.62 times 10 to the minus 34 joules times second. Frequency is what we're trying to determine. And this should say, my mistake, this should say W here. So we know the work function, we know Planck's constant, we can figure out frequency, and that comes out to 4.85 times 10 to the 14 seconds to the negative 1, or hertz. So back to the line spectrum, this is the visible range again. If we see something that is blue, what that means is blue is being reflected. And I mentioned earlier in the slides that your detector is your eye. So if something is blue, you see the blue piece of paper, it's blue being reflected from the material, with all the other colors being absorbed. So if we shine a white light on a prism, we can see that it's made up of many different colors. It's called a continuous spectrum. Just like when it rains, you see the rainbow, because the sunlight shines on the drops, it gives us these colors. So we have a line spectra, which is the emission of light at specific wavelengths. For instance, each element has a particular line spectra, whether it be mercury, from mercury lamps you get certain line spectra. Hydrogen lamps, we have neon lamps. When you go to, for instance, the club, you have certain, you have neon lamps, which you can see the white on your shirt. This is one way to determine what's the composition of a particular material. So for instance, space, a lot of hydrogen, majority is made up of hydrogen, so it gives off this particular line spectra here, you see. So Niels Bohr, he modeled the hydrogen atom where one electron, we focus only on one electron and one proton because it gets more complicated when you have multiple electrons. So we have one proton and one electron. The electron, as I said, can only live on certain levels, n equals 1, n equals 2, n equals 3, etc. So these electrons only orbit on specific energy levels, n equals 1, 2, 3, etc. If the electron is sitting here on the first level, E for electron, when it can absorb light and get excited to another level, switch the color, it can get excited to another level, so it will absorb energy if it goes from a lower level to a higher level, And when it relaxes and it comes back down to the ground state is when n equals 1. When it comes back down to the ground state, it will give off and emit energy. Here we see the corresponding change from one level to another will give us a particular wavelength. So if we, in this example, if we went from n equals 4 to n equals 1 in blue, that emission will give us a blue color in the wavelength spectrum, line spectrum. So one way we can determine the energy of the electron on a particular level is through this equation here. Again, we focus on hydrogen. E equals negative 2.18 times 10 to the minus 18. That's derived from the Rydberg constant. Negative 2.18 times 10 to the minus 18, 1 over n squared. The n is the level with which the electron lives. So here, the same equation I just showed. Remember, the electron can only live on certain levels. So as n increases, the equation shows as n increases, the higher the energy state. So if this number increases, the denominator, if that number gets bigger, the energy will get larger. If the value of n was infinity, so here, if this value was infinity, E would be close to 0. 1 divided by infinity is 0. So as you get farther away from the nucleus, the energy gets higher, where the maximum you can get is E equals to 0. So yes, that means it is higher than all these negative values. For instance, if I said n equals 5, what would that value be? Rewrite this. E equals negative 2.18 times 10 to the minus 18. The equation is 1 over 5 squared, so 1 over 25. 1 over 5 squared, if you multiply this out, you get negative 8.72 times 10 to the minus 20. So E equals 0. That's a higher energy than E equals negative 8.72 times 10 to the minus 20. So I'll just repeat, as you go away from the nucleus, the energy for the particular levels gets higher to a maximum of 0. Another equation that comes off from En equals negative 2.18 times 10 to the minus 18, 1 over n squared. We want to figure out how much energy is released or absorbed when it goes from one level to another. I mentioned earlier that if it goes from n equals 1 to a higher level, so when Ni, the initial level, n equals 1 goes to a higher level, whether it be n equals 2, 3, 4, 5, 6, this will result in an absorption of energy. You need to absorb energy to get the electron excited, and it will go to a higher state. Conversely, if the final state is lower than the initial, so if the electron relaxes back down to a lower state, you will emit energy. So let's put this equation to practice. For a hydrogen atom, what is the energy change associated with an electron going from n equals 2 to n equals 4? Is the energy being absorbed or emitted? Well, without doing any math, if it goes from a lower to a higher, we just said you need to absorb energy for that to occur. So the delta E should be positive, and hopefully it should be positive. So hopefully when we do the math, we get a positive answer. So when we plug in the values, 4 is the final, 2 is the initial. So we plug in here, 4 squared is 16, 2 squared is 4. We've written out the equation here, and we've done the work. When you do the math, you get 4.087 times 10 to the minus 19 joules of energy is absorbed, needed to go from n equals 2 to n equals 4. So I wanted you guys to try this one, so I need to pause. The question is, for a hydrogen atom, what is the energy change associated with an electron going from n equals 5 to n equals 3? So when n equals 5 to n equals 3, again, we have this equation. I'll write it out. I'll do it up here for A. We write out delta E, the change in energy, is equal to negative 2.18 times 10 to the negative 18. So 1 over 9 in this case, because 3 squared, minus 1 over 25. 25 is 5 squared. When you do the math, this comes out to negative 1.55 times 10 to the minus 19 joules. And this makes sense because you're going from level 5 to level 4, so you're emitting energy, you're relaxing down, and as a result, you will release energy here. So we get a negative 1.55 times 10 to the minus 19. Part B, is energy being absorbed or emitted? Well, the negative says it will be emitted. What is the wavelength associated with this change? So here we have to use E equals hc over lambda. If we rearrange the equation, it's going to be lambda equals hc over E. hc over E. We have E. We know h, which is a constant, 6.62 times 10 to the negative 34. We have c, which is the speed of light, 3 times 10 to the 8. We plug all those in, we get a value of 1.26 times 10 to the minus 6 meters. Just note that all frequencies and wavelengths are always going to be positive values. So you'd have to change this negative 1.55 to a positive 1.55. Another equation that we'll talk about is the de Broglie equation, which relates wavelength, so a wave property, with mass and velocity. So this is a P equals m momentum, m times v. This is velocity here. So those are properties of matter combining with wavelength, which is a wave property. So this is the equation, de Broglie, which is lambda equals Planck's constant divided by mass divided by speed. It's speed of the particular particle of interest, not frequency. So the question here is, what is the speed of the electron with a de Broglie wavelength of 300 nanometers? The mass of the electron is 9.11 times 10 to the minus 31 kilograms. So here we have to convert the wavelength to meters, which we've done here. Planck's constant in the numerator, 9.11 times 10 to the minus 31 kilograms is the mass of the electron. And we plug in the values, we get 2,424 meters per second. We also have this, you might ask, well, how does the units translate to meters per second? 1 joule, which you don't have to memorize, is a kilogram times meter squared divided by second squared. Those units will cancel out for the joule to get us meters per second. The next question is to determine the wavelength associated with an electron moving at 1500 meters per second. So here we would use wavelength using de Broglie's equation equals to h over m times v, velocity. We plug in those values. H is 626 times 10 to the minus 34 to the minus 34 joules times second. Mass 9.11 of the electron, 9.11 times 10 to the minus 31 kilograms, and the speed moving at 1500 meters per second. When you plug all this in, hopefully you get this 4.85 times 10 to the minus 7 meters. So the next topic is with using Schrodinger's equation. So here we just touch upon it. Here we have a picture of an electron going around its nucleus. So we have high regions of high density, electron density, which represents the probability of finding the electron. The electron is moving so fast, it's hard to measure exactly where the electron is, but based on calculations, we can determine that the most probable place of finding the electron is close to the nucleus. So based on the solved wave functions, which corresponds to orbitals, we develop 4 quantum numbers, which we'll talk about in the second part of chapter 6. We have the principal quantum number, which tells us the level the electron lives. Next, we have the angular momentum, which tells us the shape of the particular orbital that's made by the electron. We have the magnetic number, which tells us the orientation of the particular orbit, subshell, we could say, whether it's on the x-axis, the y-axis, the z-axis, etc. And we have the fourth one, magnetic spin, the electron spin quantum number, which tells us how the electron is spinning, whether it's going in a clockwise direction or in counterclockwise direction. And we'll talk about this again in the part 2.